Hi, my name is Emmanuel Eni and I am an application engineer at Infineon for industrial gate driver ICs. Today I would like to show you our X3 digital evaluation board, the EVAL 1ED3890, and its companion board, the 1ED38DCT. I would like to show you how to set them up, how to install the software that comes with them, and get started. But before we get started, let me introduce to you our X3 digital gate driver family. So we're talking about these two ICs here. This is our most feature-rich industrial gate driver with up to 27 different configuration parameters, 3 different address configuration, and 16 status bit registers that can be written or read over the I2C. Now, going to the rich feature set, we can split them in monitoring features and integration features to support your application. Just to give a brief overview for you guys, for the monitoring features, we have features such as fault detection and signaling via the fault pins. And this can be used to indicate internal faults such as over temperature protection, desaturation events, or switch off timeouts in the gate drivers. And we also have ready to operate signaling via the ready C pin. This generally signals events such as internal gate driver communication malfunctions, UVLO events, both hardware and software for the primary side VCC1, but also for the secondary side, both for VCC2 and for the VE2 respectively. Like I mentioned, there is also UVLO protection. So here we have 2 hardware UVLO protections and multiple software options to select from. We have pin status monitoring, where the pin state is translated to a logic signal, so you can see during the application if the on output is actually high or low. We have measurements with the internal ADC, such for VCC2, VE2, gate driver junction temperature, and if the clamp pin or the clamp function is not needed, the external temperature can be measured via the clamp pin and the built-in ADC. Now, going to the integration features, we have DESAT circuits. Here we have 2 full DESAT circuits which are configurable. We have a classic DESAT circuit that is designed to protect during short circuit, like in your typical application, what you're used to. And then we have a second DESAT aimed more at condition monitoring, where you can detect slight variation in the forward voltage drop across your switch. The DESAT circuits are sharing the adjustable leading edge blanking time, but they have fully configurable and individually adjustable filters and trigger voltages. The IC also comes with adjustable soft-off in quite variation of steps to suit all your needs, and we also have an adjustable 2-level turn-off. Here it's adjustable both in terms of the duration at the intermediate level, but also the voltage level at this intermediate level can be easily adjusted. And last but not least, we have the clamp pin, which has multiple functions. It can be used like your classical Miller clamp, or you can use it as a Miller clamp driver, so you put a smaller MOSFET right next to your module in order to get better performance. Or generally, if bipolar power supply is used, you can always use this pin with the built-in ADC to read the temperature of your module NTC. All these features allows the gate driver to be configured and tailored to the different switches, to different manufacturers, making second sourcing much easier. It enables condition monitoring for the power switches and for the gate driving circuit. And last but not least, it makes also end of production and field test of the connections and verification very easy. This makes the gate driver ideal for a lot of applications such as drives, EV charging, energy storage systems, and much more, where condition monitoring is important, or where on-the-fly configuration can bring some benefits. Now, in the industrial field, digitally adjustable gate drivers are still very new, so this is why we came up with the DCT board, which is a companion board, because sometimes the main user are still analog power electronics engineers and they don't want to really mingle into the digital world. Thus, for the companion board, we have created a really nice GUI software. This makes the development with this gate driver really a breeze, and also debugging in the application very, very easy, because the registers can be really easily read with the DCT board. For both of the boards, we have a web page available where you can find all the necessary information about the boards, documentation material, the links to the user guide, and also how to buy the boards. right now we have here the web page for the eval 1ED38X DCT. This is our companion board. And as you see here, you have the buy online button, you have the download user manual, and you also have the link to the software installation. Now let's proceed to installing the software. So we go to the link on our software repository. We have two installation options. So if you have the Infineon software launcher, you can do it via that one, or you can download it directly by clicking download. Once the download is finished, all you have to do is run the installer and follow the steps. By default, the installer will install the software on the C drive under the Infineon folder. Once you are finished, you can directly start running if you have used before any Infineon microcontrollers. Otherwise, you might need to follow an extra step where you have to install the drivers once the board is connected. For ease of use, all these drivers are found in the Infineon folder under the DCT software. So sometimes when installing the software, the drivers might not be installed, so you will need to do this step separately. The first time you connect the companion board to your computer, in your device manager, you will get a new device called Infineon 1ED3800 DCT. All you have to do is double click. Once you're here, once you're in the device properties, all you have to do is click Update Driver and then browse to your computer for drivers. You can browse it to the earlier mentioned C drive. In the Infineon folder, under Tools and USB driver. When you click OK, you go Next, and you have to accept the installation of the drivers. This only has to be done the first time in case the drivers don't get automatically installed. So the first time you install your software, you might need to also go back and install your USB drivers. The first time you connect the board to your computer, you will be prompted for a new device, which might not be recognized by your computer. So we just finished installing the software, and now we went and did a test setup. As you have seen, the boards come without any switches installed, so we installed some Infineon CoolSeq 45 milliohm silicon carbide MOSFETs on the board, and then we did the test setup. Because the board comes with a very small capacitance for decoupling, you have to provide your own decoupling capacitor, and this is what we have done. And then we did some measurements. So we're using a Rogowski coil in order to measure the drain current. We are using some differential isolated probes to measure the drain source and the gate voltage, and we're also measuring the DESAT pin voltage and the fault pin on the primary side. Okay, so now let's have a look at the GUI software. So what we do is we start the software. And this is what you will normally see once you start the software. We offer some different presets. Generally, I prefer to start with the clamp pre-driver. You click on it, you load the preset, and then you go to the quick start. Now, once you get to the quick start, if everything went well, you should have a blinking I2C light at the bottom, and everything else like the USB, the ADC, and the fault should be green. And at the same time, all of the status information is green. So for the GUI, we have the start menu. This is where you normally would start. Then we have what's called a guided mode, where we guide you to every single parameter or register that you can adjust. And we give a full detailed information here, what it means, how to adjust it, and so on. You have then the advanced mode, where we try to group a little bit the parameters, so it's a bit easier. And every time you change something here, always remember to either push the DT, which is the device transfer, or push the group transfer. And every time you change something here, you will see in the top right corner, you will see what registers are impacted and how they change. And you see here we have the input, we have the supply, ADC related, DESAT related, and many more. One really interesting part is the register view. This is for you guys. Once you finish the programming or the configuring the gate driver as you wish, you will have here all the configurations for every register, which you can save, export Send to us if you have any questions, or send to your programmer to program it in the inverter, or send it to some other colleague who will import it in his GUI and he can take over from where he left. The hardware mode is more to see in real time all the status of the gate driver, including the ADC measurements. So you see here the ADC measurements for the supply, you see the internal temperature of the gate driver and many more. And what's cool in this GUI, we actually built a PWM generator for you, so you can do static pulsing, you can do double pulse test, or you can do a fixed PWM pulsing. Now, with this being said, let's try and have a little look at what type of parameters you can adjust. The GUI is completely it's very well explained inside the user guide for the DCT board, so I will not go into every single detail. I just want to show you some of the flexibility of this gate driver that is enabled through the eval board. So now let me just show you a double pulse test with the default settings. Let's look at the DESAT and the default settings. So by default, the gate driver comes with a DESAT set to 9.18 volts and a quite short filter at 220 nanoseconds, and the DESAT 2 function is turned off. And we're going to leave it like this. Let's go into the hardware mode, and we go into the double pulse mode. I start the power supply. I'm charging the power supply to roughly the DC link to roughly 500 volts, and my inductor is in the range of 100 microhenry. So for the first pulse, I'm going to do something in the range of 20. I'm going to leave the pause between the pulses at 3 nanoseconds, and the second pulse I will put at 3 microseconds, sorry. So if we do now a pulse, you see on the oscilloscope some nice waveforms. So we have at the top, channel 1 is the fault signal. On channel 2 we have the DESAT signal, so you see the DESAT increasing. Channel 3 is the VGS. VDS is with green on channel 4, and on channel 5 with the orange we have the drain current. Now what I can do is I can try and increase. So I can increase the second pulse on the PWM generator, and I'll put it to 15 microseconds. This is, by looking at the DESAT, I can tell it's already quite at the limit, so this should trigger a DESAT event. So if I pulse now, you can see here I have a DESAT event, and if we look now on the oscilloscope, we can see the gate, the VGS, right? We turn on here, and we are less than 2 division, so less than 8 microseconds when we set it to 15 microseconds. Now, what can I do is, let's play a little bit with the DESAT, so we see if we can actually force the DESAT to trigger earlier, or if we can play with the filter a little bit more. Okay, so I'm gonna go back. So one cool thing which you can see is once a fault event happens, the GUI will automatically turn off the PWM generator and the fault goes on. And you see here, this is the fault signal, so it tells you have a fault. And the ready status is not ready because we have a gate driver internal status. So if we go and look at the fault events, we see there's a red button here which says it's a DESAT 1 event. So we can even understand what happened and why it happened. To clear this, we just click on the fault, and when this is cleared, all the faults are cleared. We go back into the advanced mode. One thing we can do is we can take the filter. So we increase the filter, let's say now by 2 microseconds. To 2.275 nanoseconds. So we remember we have to program it, and then we go back into the hardware mode, and we do again a double pulse with exactly the same settings as before. And keep in mind, we trigger the DESAT in less than 8 microseconds on the second pulse. So now if we do again a pulse, if we look back on the oscilloscope, what we can see here is that our DESAT event now went to closer to 10 microseconds. So it increased by 2 microseconds. So now I resetted the fault again, and if we go back, let's try to lower the DESAT voltage. So until now we were triggering at 9.18 volts. We can make it to trigger at, let's say, 4.99 volts. We remember program it, and we go back into the hardware mode, and we try again the double pulse test, and we do again the test. And what you can see here now is actually in the first pulse, we already hit this 4.99 volts. So the DESAT is triggered, the gate driver is turned off, and no other pulse is registered. So even if our microcontroller does the second pulse, because the gate driver is in the DESAT mode, until it gets resetted, it will not propagate the pulse on the output. Now, we had a look at the DESAT. Let's look a little bit now at the turn off. So what I want to show you guys now is I want to show you here the fault off, the soft off. So until now we were shutting down with 7.2 microseconds. So you will see this in the oscilloscope here in the turn off ramp. You will see the soft off current impacting there. So right now, let's say you have an application where your gate, you're turning off too fast and your current is very high, so you're avalanching, or you're close to the limit of avalanching your switch, or you're desealing. So what you want to do is you want to slow down the turn off. So what you can do is you can take the soft off current and decrease it. And just for demonstration purposes, I'm going to decrease it to 0.7% of the nominal current, just because you will easier see the impact of this. So I go back to hardware mode again now, and we do a pulse. One thing to pay attention is you can have a look here on this edge. So this is from the previous pulse where we had close to 7%, and now if we do one with 0.7%, you see the slope became much longer. So the IC turned off the silicon carbide MOSFET much slower. And you also see this in the green waveform, because now the overshoot is much less. Of course, if your application can't use a soft off, we have an option to do a 2-level turn off also. So let me reset again the fault. I will go back, and now I'll say, okay, the fault turn off, I don't want it to be a soft off, I want it to be a 2-level turn off. Remember, program it. And now we go in the output section, because this is where the 2-level turn off is placed. So what I can say now is I want to do a 2-level turn off. I want an intermediate voltage level, let's say, to have it at 8 volts. I want to stay there for 3 microseconds, and I want some slower slope, so let's say 15 volts per microsecond between the on and the intermediate voltage level, and then I want 60 volts per nanosecond for the second ramp from intermediate voltage level to off. Again, these are just for demonstration purposes, so I want for you guys to really see this, how it impacts your waveforms. In reality, you have to adjust this for your application. The nice thing using the X3 Digital is you can have some preliminary settings where you put your product out on the market, and then in 6 months, 1 year, if you see you have some margin to play with these parameters, you can always change them, verify them in your lab, and push them as a firmware update to your application in the field. So going back now to the hardware mode, let's do a test. Remember, now on the scope you have the soft off. Now we're doing a 2-level turn off in the next pulse. So you see here the 2-level turn off. So you see we're at 15 volts here. We're turning off with a 15 volts per nanosecond ramp. We're staying here at the intermediate voltage level for at 8 volts for approximately 3 microseconds, and then we have a 60 volt per nanosecond ramp until the turn off voltage. So now what I want to show you guys is the DESAT 2 counter, or the DESAT 2 function. Like I mentioned, the DESAT 1 is for typical classic short circuit protection. The DESAT 2 is more for condition monitoring, where you can count partial overload of your switches. So you think, let's say in a drive application, you have your motor winding a bit leakier, and then it increases the current on your switches, and things like this. So generally, let's say we put the DESAT 1, let's say, to 9 volts and 2 microseconds, and then we put the DESAT 1 lower with a longer pulse filter. We increase the counter, let's say, to 5, and we remember to enable it. We program this, and then we go back to the hardware mode to do some more double pulse testing. What I want to do is I want to actually decrease the secondary pulse, so I'm not triggering a DESAT 1 event, so I'm going to decrease the second pulse to somewhere around 5 microseconds. So now we do a pulse, and we see on the oscilloscope that the 2 pulses, let's say, went through, and what we can see is we have a DESAT 2 event counter. We do again another pulse. The counter increased because only one of the pulses is long enough. So one pulse is 5.3. So it might be not long enough to register on the DESAT 2. But you see the counter went to 2. Now we do another pulse, went to 3. So basically it's counting the first pulse. The second pulse is not really detecting. We go to 4. And once we will hit 5, you will see it will stop on the first pulse, or at least on the scope, it should stop on the first pulse, and the second pulse should not propagate. So let's see what happens. We see here in the GUI, we have an event, there's a fault, And if we look, it's a DESAT 2 fault because our counter now reset, but we know our counter was supposed to be 5. If I now look on the oscilloscope, I can see my pulse stopped on the first PWM, which confirms that we had a DESAT 2 event. Even more, you can see that we have a 2-level turn-off, which means really it was a fault off triggered by the gate driver. So that concludes our video on how to set up and get started with the X3 Digital. For more information or to purchase the boards, please visit our website. And if you have any questions, be sure to check out our Infineon developer community.